Hello everyone, this is the a video for the Keras and Keras-Mlp lab. Again, my apologies for not delivering this on Thursday due to the circumstances that I explained. Okay, so we will start with the file that is uploaded on Moodle, and I will take you step by step through it. The plan is to explain this in the video. This would be helpful to the other group as well, and then we can arrange a Teams meeting or even a face-to-face meeting for different groups if you have more questions, so I can take you through this on a more personal level. Alright, with that out of the way, we'll start with downloading this file from Moodle, P6 Keras. Keras is a framework that allows deep learning and neural network architectures to be designed and implemented. You can train so many things with it. It was originally built on top of another framework called Theano, but this was outdated about 3 or 4 years ago, and eventually they uh, pivoted to using TensorFlow from Google as the backend uh, for Keras. During that time as well, Keras also adopted the same interfaces with that sklearn is following, so .fit, .predict, and so on. And this made things a little bit more easier as a learning tool in terms of deep learning and neural network work. Alright, so we'll start with identifying what kind of modules that we have here. I'll first import from sklearn model selection the train test split. This is the normal thing that we know, and also NumPy for some of the mathematical things we do. You can import Keras using import Keras, and from that has several submodules. One for the layers, one for the loss functions, and one for the optimizers. There are other submodules, but these are the ones we are using now. It also has another submodule called models, and from this you can import different types of models. We will use sequential. This is the normal one that we usually see in all in our slides, which is layers are stacked on top of each other. This is what makes it sequential. One layer feeds to another. There is functional, which means I can have access to some of the loss functions or activation functions to use them separately, independent from being a layer. And there's also a model, and this is basically a way to say, you know what, my inputs are starting from this layer, layer X or layer X1, whatever, and my output will be at layer X10, and it will wrap these layers into a model and then use this model as if it is an sklearn model or a Keras model, so you can use it very easily in many ways. Cool. With layers, we have an input layer. This is an important one. This is what defines that my data will go through this layer. Your model usually starts with an input layer first. There is a dense layer, which is the multi-layer perceptron, just neurons fully connected to each other. A convolutional layer, this is for images. We'll see how we operate with this here. Max pool, this is a pooling layer. The max pooling layer, which means it will iterate in a moving window and select only the largest activation in each from all the neurons. And now this is a two-dimensional one because we will be using it with the convolutional 2D here in classifying numbers. There is also a dropout layer, which, as you know, just zeros some of the outputs from the neurons randomly, and with that you can have more resilient model. Flatten here, this layer is more operational or procedural. It doesn't really do any mathematical operation, but what it does, it takes a 2D layer or 2D feature map and make it in 1D. We usually use the flatten layer before going in from the convolutional part, which is the feature learning part, to the multi-layer perceptron part, which is the classifier or regressor part. And so on. This is another way of max pooling. We'll see about that. The next set of layers will be the activation layers. We have a relu function, which is 0 for any input that comes before 0. And any negative input will be capped to 0, and then it goes linear after that. Preload is a reload but has a parameter that can be optimized or learned rather during the process. Softmax is the e power x over the sum of e power x to all the neurons. This is what we use for classification. This is instead of having multinomial logistic function there. There is also tanh, and you can add sigmoid, whatever functions that you would need later on. Loss functions. We have mean square error. This is the normal one we've been using. Y minus y hat all squared, and then you sum and average by number of samples. There is mean absolute error, which is y minus y hat, but it's not squared, it's going through an absolute operator, and then again you divide by number of samples. Optimizers, these are the training algorithms that you will be using to train your model. SGD here is the stochastic gradient descent. It has some of the parameters that it have include also momentum, and then also Adam, which is another optimizer that we discussed in the lectures. And the way it works that you start with a very small learning rate and let the momentum pick up over time. Finally, we have some utilities. We're just using one of them here, which is the categorical. The reason we need this function is that the way we expect data coming to softmax, or the output coming to softmax, would be a distribution of some sort. So we need to map all the labels. If I have 3 labels, I do not want to have these 3 labels listed like 1, 2, and 3, but rather for a particular sample, if it's label 1, should be 1, 0, 0, and this would be label 1. If it's label 2, then it should be 0, 1, 0, and then label 3 for us would be 0, 0, 1. And then when your network or your model is trying to learn is to actually maintain this distribution, it has to add to 1, and this is what softmax does for us. And at the same time, it will try to maximize the number, the probability that's coming for this particular label. This way of encoding labels is called one-hot encoding, and this is pretty much the adopted way to use to do with classification in terms of deep learning and neural networks. Okay, with that we'll go into task 1. Close so many things. So this task is fairly straightforward. We have a bunch of coordinates x1, x2, and the goal or the objective here is to determine whether these 2 coordinates will fall inside a unit circle or outside a unit circle. A unit circle means it has a radius of 1. So the idea here is when I feed these 2 numbers, any 2 numbers, into my model, it should give me a negative 1 if the point of these coordinates would fall inside the circle, or a positive if it falls outside the circle. Okay, so we'll start by defining our model. So our model is a sequential model, so this is why we imported sequential from the models here. And we'll just give it a name, my model, whatever. You don't have to specify a name, but I found it very an easy way to remember things, because you will have so many models interacting together. You're chopping, changing between different models. You probably need to know the name of each model and each layer there. Now, our model will add the first layer, which is using the add method, and our first layer is an input layer. And this input layer will have to define what the shape is. And the shape, because we have two coordinates expected to go into this model, so the shape will be 2 and comma. This is a univariate tuple. Usually when you have a tuple, you can define it like 2 and 3, like this. But if you want to define only one coordinate, but keep it inside the a tuple format, you have to add an extra comma there. And if you do it without that, it will just return to it. Assume that you are evaluating this expression. So when you have this, this is now a tuple, and you can verify this by asking what the type is of this. Cool. And we'll give it a name input. Now our next layer would be a dense, and it has only one neuron, and it has an activation function sigmoid, and we'll give it a name called output. Now I have a question here. Is sigmoid the correct function here? When you think about this question, you have to check what is the dynamic range of the sigmoid. What is the maximum and minimum values that you have that the sigmoid function actually produces. So with that, we'll just go into um, Desmos graph or whatever. By now, you should already have memorized this whole thing. I think this should be negative and so on. So our maximum here is from 0 to 1, and we already know that. But we want to map things between -1 and 1. So you have a couple of ways to do this here. Either you scale this sigmoid into a bigger frame and then subtract 1. This would be one way to do it, or you can use one of the functions to that actually does that, or I think the tanh would do that. So that's the way to really think about answering this type of questions. Now, if you do it with the tanh, so if you replace this with tanh, everything will go smoothly because everything tanh is already an operator or a function that Keras knows about, and it has already pre-calculated the derivatives for you, so things will be much easier. If you change the function, then you have to use a different or a custom layer that can do that for you to accommodate for the different um, for the type of derivatives that you do. In this case, it doesn't really matter that much. You're just scaling and maybe subtracting 1. But if you use more complicated activation functions, then you have to provide a derivative for that. So the answer to this one would be no. Tanh is the correct one. Now, after you define your model, you can print a summary of this model. It will print down here, and then you have to compile the model. It will not start training unless you compile your model. The reason for that is that Keras and TensorFlow are using what's known as graph model in terms of connecting layers and neurons and derivatives together. This is more efficient way to to there are different algorithms to reduce the graph and maybe save you some couple of calculations that you did not really need. The other way to do that is that to have everything just written as code, and then you bear the responsibility of actually optimizing this. PyTorch does it the other way. It is more useful in terms of research, but eventually when you go to production, when you want to actually have a model that's deployable on any platform, this includes cloud by the way, you eventually have to go through the process of optimizing your model, and then you will end up using a graph model like this. When you compile your model here, you have to specify what kind of optimizer you want to use and what is the loss function you are using. So we are using the mean square error as a loss function. Notice here that I can just put it as a string here because these are already predefined inside Keras. But if you want, I mean, I can replace this with the Adam like this, or you can add the actual object, optimizer object Adam, and then you specify the learning rate for that, momentum, and other parameters. Alright, so this should have our model. Now we can probably stop that and then let me run it from the start. We'll run the tench is not one of those. So now we have, so tench is not predefined as a separate layer. That's what this error was. Okay, so we have imported everything. Now we have our model. We can run this and it should show us a summary of our model, and there it is. So my model, and that has one layer. We called it output, and it takes one. Sorry, it produces one result, one value out of this. The none before that one is mainly referring to the batch index. So if you're feeding 10 samples at a time, this would be 10. But when you print the model, it's printed by none because this is allocated during the training part, not during the designing of the model. Now we have three parameters to optimize. These three parameters, can you guess what they are? Basically, we are taking two inputs. This means we have two weights, and we have one neuron, which means we have one bias. So this is all in total three parameters to optimize. And it will give you a summary down there, the total parameters and number of trainable parameters, because sometimes you can lock few layers from training, and this would be something that we will discuss in future labs. And it will so this summary will give you number of parameters you are training and number of parameters you are not training. You're just using it as it is. The main idea of locking parameters is that if you download, say, a pre-trained model from, say, Google or Amazon or anything, then you can lock these parameters and then you add new layers on top of this to make the model do what you want to do. So maybe it was designed for a classification, you want to use it for regression, but you need to use the same features it already learned. This is why we might need to lock some of the layers. Okay. Next step would be to prepare our dataset. So we'll prepare, say, 10,000 random samples of x1, x2. This is usually done using NumPy, random randn, which is normally distributed random number generator. We'll take 10,000 samples and we'll take two values for each sample. The next one would be to define our y, our target. This would be -1 or +1 based on that. So in this we need to have a function that will pass access to it and then will give us what the values are. Alright. Now your code goes into this function, and this is basically a very straightforward thing. Basically what we're saying is x0 squared plus x1 squared minus 1 should equal 0. This is the circuit equation. And we are going to implement that. So let's make a return value here equals. So these x0 and x1 are coming into x's, and the x's have two values. So we can easily say x's power 2, and then we'll wrap this into a bracket, and we'll sum that at x is 1. And then we'll subtract 1 from it. And we'll return RTN value. So the main idea here is that the values, the two coordinates are already there, and what you need to do is just square both of them and then subtract 1. and you need to sum across all the variables. The reason I made it as sum at axis 1 is that, let's say if you make it 3, now you are talking that these points should be inside a unit sphere. If you make it 4, it's inside a 3 sphere or 4-dimensional sphere, and so on and so forth. So this is the whole rationale why I am using it this way. Let's give this a try. So let's run this and we'll see what we have. So our x's are, oh sorry, x's, really? X. Our x are values like these, and our y should be values like this, and each value of this would be these two squared, added together, and then -1 at the very end. Now let's try what I mentioned before. Let's try do it this way and make it a sphere. Now the x would be something like that, and then the y, we need to do the y again, and then the y will be again same values there. Okay, so this should be working very nicely. Now we have our data, we have our model, we have our data. Now we need to train our model. Now before training we need to train test split, so we'll have the x, y, x and y, and we have a test sample size of 15% or sample ratio of 15%. And then basically what you do is model.fit, give it the train x, train y, validation data, you give it val x and val y, batch size, this is the mini batch size. Remember when we talked about SGD, the stochastic gradient descent, and why it needs a mini batch of the data is that it needs to evaluate the error as a whole, not one sample at a time. If it's doing it one sample at a time, it will be very hesitant to take the correct move into any direction. And the number of epochs, epochs means number of iterations throughout the whole data set. So if you have 10,000 samples and your batch size is say 1,000 samples, then each epoch will have to go through 10 iterations until it finishes. Verbose here is mainly just for printing what we hear, the status of the training. With that, let's run our model. Let's run the data again because I changed some of the things when I played here, and then let's run the training. Now when you look into this, what it's doing is mainly going for 10 epochs. Each epoch will go 8,500 iterations, and the 8,500 is because we have 15% allocated for testing or validation, and these are the values here, the loss values here. So with each epoch here, it will say the loss, this is the training loss, and this is the validation loss. So this is the loss that's being calculated so far for the training samples, and this is what's being done for the validation samples. Now the model does not train on validation samples, so this is supposed to be a little bit higher, but because we do a lot of regularization inside, and even if you add dropouts, you will have more loss on the training than the loss on the validation. This is for a healthy model. An unhealthy model, you will find these losses dropping very quickly, but these losses are growing up. This means that your model is memorizing the training data and it's failing to generalize and work with unseen data, which are the validation data. Okay, so far we have a very, very bad model. This is a huge loss in terms of training and validation. So what we can do is just let's give it some more time and see what it can do, and maybe we can evaluate more samples at once. and we'll give it a run. You can see the error is actually dropping there a little bit. Let's see if more time will give it more better evaluation. Bear in mind here I'm doing a control enter to run this block. The model has not been reinitialized, so it's still updating on the weights and things that it learned before with previous ones. Okay, so our model finished training, and it's really clear that it's not really getting any better. There is no um, way to make this model train better. And this is for a good reason, because we are just using only one neuron. Basically, what we need is maybe have more layers or more neurons. Now, we cannot change this parameter because this parameter is our output, but we can add new layers. So we can add model dot add another dense layer, and then we'll give it number of neurons, say 10, and let's give it a name equals hidden. So notice that I don't need to specify the shape here because this model is sequential, so whatever output shape coming from this layer will be the input shape of this one, and the output shape of this one will be the input shape of that one, and so on. So this is how it builds itself because it is a sequential model. If you are not using sequential model, you're going to have to specify what the shape is, what the input shape and output shape is for each layer, and we'll see examples of this when we work with when we work with the actor-critic model in Keras-Mlp. Okay, so we have added a new layer and we give it a 10 neurons here. So when we run that, notice the summary now is saying that we have a hidden layer, and this hidden is actually the name of the layer here, and the output is 10, and now we have 30 parameters to optimize. We have 11 parameters here. In total, I have 41 parameters. The way you think about this is that these this output layer will have 10 inputs plus one bias, which are this one, and then you have two inputs going into the hidden layer, so this would be 20 plus 10 bias would be 30 parameters to optimize. In total, we have 41 parameters, all are trainable, non-trainable. Now the next thing, we will again generate our data, and let's try and train that. Okay, the error is dropping a little bit. It is not as at its peak, but it is doing something. Okay, now it is stale. You can terminate it by Control C to interrupt it, and then we can maybe add more hidden layers. So you can add 1, 2, 3. Now you can see how it can be tempting to actually make the model initially very large. I don't really like to do it this way, because eventually things will get out of control, and then you have to re-optimize your model again. Update the data, and let's do the training. And the error is not dropping as much. In fact, you have more error here because you have more parameters to optimize and learn over there. This brings us to one very important point, which is the values trained here may be larger than what the network can handle in terms of how the gradient is being calculated. So let's investigate what the x's are and then what the y's are. Now we have very large values here, 4.7. When you have these kind of values coming into the neural network at either ends, this means this affects the gradient that you have. And remember, you have a mini batch of 1000, so this can get the gradient very, very high. So you can either scale down these ones, and this is what we did before when we did the data exploration. Either we use standard scaler or we use a min-max scaler to just squeeze it between 0 and 1, then the network will start behaving better. Or you can actually modify the way your data is being evaluated. For example, the main objective that was that we have -1 and 1. We're trying to do this as a classification in terms of a regression type of thing. So we can say y sub y less than -1, less than 0 would equal -1, and then y where y is greater than 0 will equal +1. Now when we do it this way, if we check the y's, it will be 1, 1, -1, 1, 1, -1, and so on. This should have all the values already close enough to where the tangent is. The problem with the other range of values that you can be, your y could be somewhere here, or the y hat could be somewhere at, say, supposed to be at 100, but it is capped to 1, so that's why the error can be unrealistically high. And let's run this one. So now we have a new new data set, and then we can play that. Now you can see the error is actually dropping really nicely. We are below 1 now, and it's keeping dropping as well. Now one thing we can do here is to maybe increase the learning rate a little bit. And let's run this one, run that one, and run that one. Alright, so it's clear it's not learning. It's as if it starts dropping a little bit, but it does not eventually get any momentum. It's almost similar to the point that the rolling ball is actually on a flat surface. There are no gradients, there are no updates. And there is a good reason for that. And the reason is, if we go back to our model here, we defined dense layer, but we did not define any function, any activation function. Meaning that we don't actually map whatever values that we have input. It's almost like you're just multiplying matrices and that's it. And this is not enough to make the model trainable. So now we added an activation function for these. And start training again. And there we go. The error is really dropping now. Very nice. The learning rate is fairly high, that's why it's jumping up and down. But it's going in the right direction. I think I jumped all the way here. Now, when you see the error is fluctuating between two values here, this means your gradient is too high and will probably mean that you have a very high learning rate. Remember, with Adam, we have to start with a very low one and then get it running. So now the error is dropping fairly slowly, but it is fairly consistent. We're still jumping here, but it's going to below 0.02, which is nice. And now we are at double zeros after decimal place, and we're almost at 1000 epochs. There. this is a healthy model. This is a very successful model that has been trained. Now, the overall training loss was 0.0072. Validation is at 85. This should be lower than the training, but we did not add any dropouts to actually do that. Alright, so we have a model. We have a model here which we can predict some values. So basically we want to say if we numpy.array, if we pass a value of say 1 and 1, it should give us what the output is. And the output would be 1 here because you will be at the circle or maybe above it. Remember that when we did the data here, we said less than 0, above than 0. We didn't really work out the case when you're actually touching 0. If you would do it this way, y equals 0, you can have a third class there, but the problem with that is that this class would be very small compared to the other two. You have a big chunk inside, big chunk outside, and just a slither on the surface. Okay, so let's try something that is really small and see if it is inside the circle, and it's giving us -1. This is brilliant. So now we have a model and it does predict, it does do what we want, what we trained it to do. Now let's dissect that model. Let's see what's inside that model. So we have our model. You can say get weights, and this will give you an array of all the values or parameters that got estimated or got learned inside. You will see they are arranged in terms of weights, biases, and so on. So let's check that. Let's call this W's, and if we have W sub 0, this would be, and let's check the shape, this would be 2 because our input is 2, and 10 because we are feeding 2 values into 10 neurons. Now if we do this at 1, this would be only 10 because these are the 10 biases for the 10 neurons here, and so on. Let's take 2. 2 would be 10 going into 10, so this should be 10 by 10, right? And 3 should be the biases for the second layer, which should be 10 values. Third one would be 10 by 10 because this is from hidden layer 2 to hidden layer 3, and we have 10 biases at the very end. Now the last layer should take input of 10 values and output of only 1, so this should map to 10 by 1, and the bias for this one should be a single value because we have a single neuron at the very oh, this is not correct. Oh, I chose the wrong one. 7. Yep, 1 bias for the last neuron. Alright, so now let's do a little bit of a trick to see how things work. Now if we wrap, let's make an input value, say x1. This is the first sample of x's. This would be a numpy array dot matrix, and we'll give it say 0.1 and 0.1. So this would be our sample. Now let's get the weights at the very first layer, ws sub 0. We check the shape. This should be 2 by 10. So we can wrap this into a matrix, np.matrix this, and we probably need to give it a name. I'll call it W0, W1, whatever. Now let's get the bias for this layer as well. So we'll call it B1, and this would be at 1. My apologies, this should not be shape, this should be just the shape here. So now we have W1 dot shape is 2 by 10, and we have B1 dot shape is 1 by 10, and we have the X1, the first sample, which is 1 by 2. Let me see what X is. Yes, that's correct. So now we can have X1 multiplied by W and plus B. This should work and give you, sorry, that should not work. This should work and give you really 10 values, because you have 10 neurons or 10 outputs coming out of this layer. Now if you take these values, multiply them by W's and B's for the next layer, and then take the other values, multiply by this, and so on, it should give you the final result. To illustrate this, we are going to simplify our model. Let's take it this way and make our model really tiny. We don't really have to train it all that long, so we'll just do 10 epochs to get the values there. Okay, so now we have W's equals np model dot get weights. So we have W's here, fine, and then we have our X1 equals same thing, and we will have our W1 equals W sub 0, and while we're at it, we'll do the B1 as well, W sub 1. So we'll have W1 dot shape, if I can spell, and we have B1 dot shape. Sweet. Now let's take the W2 and the B2. This would be from 2 and 3. Now W2 dot shape and B2 dot shape. Okay, now let's do our where did we do that? X1 times, yep. So we'll do this by W1 plus B, and we will feed this, because this will be multiplied by W2 and then plus B2, and we'll give you a final value here. Now this value is not really that correct. If you use the predict variable, it will not give you the same value, because we did not actually apply the tanh here. Let's do this linear. W2 and W1. Now let's do that, and let's see our model dot predict X1. same value, same value. That's it. So you see, it's all about the how the data is arranged in on the input side and the output side. You have a bunch of matrices that are being learned, and all you need to do is just multiply the input by sequence of matrices. You add the bias, and it will add up all the way to the same value. If you want to apply the activation functions, you can still add wrap this into a tanh function and then wrap the entire output into another tanh function. This will give you the exact output as if you're using tanh. In this case, these two values are exactly the same because we replace the tanh or the activation layer by a linear function. Linear function is mainly f of x equals x, and that is it. So I hope this really helps on understanding how different parts of the neural network is working, how to make your model, how to change different parts of it, and you have seen now how the model is trained and also what are the parameters that got learned inside here. Now bear in mind here we doing this whole thing numerically, so this is different from the style that we did with SymPy before. With SymPy you let the machine do the derivatives for you, and then you have to do the algorithm to actually train with that. In this way, this is more streamlined process. It's already doing all the derivatives for you. It's been already pre-calculated. This is part of the framework. All you need to provide is just input data, output data, and make sure that there is a relationship between the input and the output. In our case here, it was the circle, the equation of a circle. In your case, would be mainly the the kind of things you're trying to predict, which is your output, in comparison to the kind of data that you already have as an input. Doesn't matter if you're collecting this data from a mobile phone or from internet or from a data set. This is the entire mechanism of actually working with neural networks and deep learning in general. I'll see you in the next video when we talk about the convolutional layers, but this should be a very good start on how to um, get started with Keras and neural networks. Thank you. Bye.